4.2, day 4, we're talking about blocking and experiments. The first example says SAT schools. Many students enroll in prep courses to improve their SAT scores. 20 students who have taken the SAT once volunteered to participate in an experiment comparing online and classroom prep courses. Describe how we can use a completely randomized design to compare online and classroom SAT prep courses. Okay, so questions like this on our test or the AP exam, the first thing you need to show how to do is how you're going to randomize all the participants, and then just describe thoroughly how you would conduct this experiment. So the easiest way to randomize these things is the hat method. So if we can put the 20 individuals, if we can put their names on identical slips of paper, put them in a hat, mix them up. So place the slips in a hat and mix well. Okay, then how are we going to draw students' names? If they're present, I guess you could have each student, well, not each student, but you could draw one at a time and put one in each group, like you're dealing cards to two people. Or another way, if you mix them up really well and it's really random, you could just draw the first 10. So just draw 10 names, and then those 10, we can just assign them to the online group. They can be the treatment of the online class. And then the remaining 10 that didn't get pulled, those 10 can be in the regular classroom. So that's still technically random because everyone had a chance to be in both groups. Okay, so you assign people to treatments. They do the study. They go through each class. They take the SAT, and then what do we want? So we're going to record. We're going to observe the score improvement for each group. And once we record that, we observe that. Our conclusion. We're going to make a conclusion about which group was better. So which treatment worked best? So I try to write this in as few words as possible. Randomize it, assign it to treatments, what are you going to look for, and then what are you going to make your conclusion about? So part 2 gets a little more specific. It says among the 20 volunteers, it's going to talk about their math class here, 10 are in pre-calc, 6 are in algebra 2, and 4 are in geometry. So we're specifically going to look at their math improvements. And then it says, what problem does this cause? The fact that they're in different math classes. And then how can we address the problem? Well, first we were just trying to compare online scores to regular classroom scores. This adds another variable to the mix. You've got kids from different math classes with different math backgrounds. So that creates another source of variability. So I'm just going to scroll down here. So students with different math backgrounds could create a large amount of variability. Who knows, maybe the kids in the pre-calc course don't improve very much because they've already got all the math, and the kids in the geometry course improve a ton because they learned so much in that prep class. So that's the point, is adding another variable to the mix. Well, that creates a problem because that could be a large amount of variability for us. How do we address it? Well, originally we just wanted to compare online versus classroom style. So now we're going to have to look in each group and do a little experiment in each one of online versus classroom. So that's similar to, you could say, stratifying if we were talking about samples, but we're not talking about samples. So now we have two variables that might influence the response. So this creates difficulty, like with distinguishing what the effects really were. Was it because of the online classroom, or was it because this person was already in geometry or pre-calc or whatever? So here's the key, and this is the key vocab term for today. We're going to block on math class. So that's what our experimental vocab. We're going to block on math class, which basically means we're going to look at each math class and conduct the experiment within each class. So within each class, or within each block, you could say, it's like within each group, randomly assign the treatments. So basically go to the pre-calc group, those 10 kids, and then randomly assign 5 kids to the online class, 5 kids to the regular classroom, and so on and so forth within each class. So then we don't have different classes being mixed up in our results and then creating more variability. Okay, so part 3 here. It says here are the actual results of the experiment using math level as a blocking variable. Make dot plots to compare the improvements of the students in the online course versus the improvements of the students in the classroom course. And then based on those dot plots, does there appear to be convincing evidence that the online course is better? So these are really easy numbers over here. And you can see which kids got the online, which kids got the classroom. So let's make this dot plot really quick. So I'm going to go from 0 to 100, cut it in half at 50, and then cut that in half, so on and so forth, so I can get 0 to 100. I'm going to mark every 10. And then I'm going to label this axis. This will be score improvement. And we're going to make parallel dot plots here. So I'll first put the online class, and then above that, I'll put the classroom dots. So for the online class, let's look at that first group. We've got 100, 100, 90, 90, 100. So I'm going to add those dots in there. And then some classrooms. Here we go, some more online. So 50, 60, and 40. Add those dots. And then the last 2 onlines here are both at 30. Okay, so right above that, let's do the classroom dot plot. So this will be parallel dot plots. They're going to be using the same exact scale. So for the classroom, the first group, let's see, 70, 70, 80, 80, 80. Let's put those above right here, 70, 70, 80, 80, 80. So it's almost like you could draw a dotted line, if you really wanted to, underneath here. Just kind of keep things straight for yourself. I'm not going to use one though, because I already made this graph. And then the rest of the classroom people, so 30, 40, 20, and then 0 and 20. All right, so there's our dot plot. That's our parallel dot plot. Based on this dot plot, does there appear to be convincing evidence that the online course is better? So I hope that this doesn't convince you. So now you've got a visualization. I hope that that doesn't convince you. I mean, yeah, we've got some people up here above, but then there's also a lot of improvement here in the classroom. There's a ton of overlap. So maybe like the general trend shows online is better, but this really isn't convincing or even statistically significant, we should say. Like that's not convincing evidence that online's better. So there's a considerable amount of overlap, which means this doesn't show that there's a lot of difference. So there's not that much difference. So the comparison's unlikely to be statistically significant. Okay, so the next part, I've already got a dot plot here made. It says dot plots, and number 3, ignored the fact that we blocked by math level. So it just compared online versus classroom. Here's the dot plot again, but now it's got different symbols for students in each math level. So these triangles are actually pre-calc kids. And the gray circles here, those are Algebra 2 kids. And then the squares that are blue, those are geometry kids. So it says, notice that within each math level, the online students clearly did better. We couldn't see this difference when we ignored the blocks. The average improvement for students in pre-calculus was a mean of 86. For Algebra 2, the mean was 40, both pretty big improvements. Geometry, the average mean for improvement was 20. How can we use this information to account for the variability created by differences in class level? So basically, how can we compare across the board? For online class or for the classroom, how can we compare across the board? Because there's 3 different classes going on. Well, right now in this dot plot, the lowest possible improvement you could have gotten was obviously 0. You didn't improve at all. But if I want to be able to compare among the 3 classes, obviously pre-calc improved the most, geometry was the least. I need to give myself a baseline for what the average improvement was. And since the lowest improvement was geometry at 20, I'm going to use that to adjust the rest of my scores. So let's assume that on average, everyone improved 20 at least. So that's how we're going to adjust our scores. So to compare directly, we're going to adjust the data points. Okay, so scrolling down here, now we're going to have a baseline. Since the lowest average was 20, geometry was an average of 20. To be able to compare that, well, with pre-calculus and algebra 2, I'm going to use that for my baseline. So my baseline is no longer 0. The lowest improvement average that we saw was geometry, and that was a mean of 20. So I'm going to use that to adjust all my scores. So if I compare everything to the geometry mean, like if I compare, let's start with algebra 2. If I compare my algebra 2 scores to geometry, so algebra 2, the mean was 40. Geometry, the mean was 20. So if I compare algebra 2 to geometry, my new baseline for algebra 2 would basically be 20. So instead of starting at 0, if I start at 20, this would now become 20 on average. So what does that mean for all these scores? We're going to fill these boxes in. For the algebra 2 students, you're going to subtract 20 from their score. So that's how we're going to compare them. If you subtract 20 from each algebra 2 student. So that's how we adjust the algebra 2 scores. Okay, let's do the same thing for pre-calc. So if we compare pre-calc to geometry, which is our baseline, so pre-calc transformed into geometry. Pre-calc had a mean of 86. That was their mean improvement. Geometry again had a mean of 20. So now since we're using 20 as our baseline, we're basically going to subtract 20 from all the pre-calc scores. So subtract, not 20, I mean 66. What's the difference between 86 and 20? 66. So subtract 66 from each pre-calc score. And then when we're done, it'll actually make sense to have a dot plot of online students versus a dot plot of classroom students, because then they'll all be adjusted. We can make a fair comparison. Okay, so let's go through and complete this table. It should be pretty easy math. Subtract 20 from the algebra 2 kids. Subtract 66 from the pre-calc kids. The geometry kids, their mean is already at the baseline. Their mean is already 20, so you don't have to subtract anything from them. So back up to the top of my list here. This column, that's going to be our adjusted improvement. So to account for the differences between the three groups, our baseline is no longer going to be 0. Our baseline improvement is going to be at 20. Okay, so the first person is a pre-calc student. So this class P stands for. So subtract 66 from their score, like we said. Their adjusted improvement is 34. Same for the next kid, pre-calc. All these kids are pre-calc, so subtract 66 from their score. Scroll back down. Pre-calc, pre-calc, pre-calc. So go ahead and subtract 66 from all those kids' scores. And then the next group here has A, so that's the Algebra 2 kids. So we said we're going to subtract 20 from each of their scores. So 30, 40, 20, 10, 20, and 10. And by 10 I mean 0 for this kid right there. And then the last group, geometry. Since their mean was already 20, we don't have to do any adjusting here, because we adjusted everything to our baseline mean of 20. So basically we subtracted 20 from all these people. For an Algebra 2, 66 from all the people in pre-calc. So geometry, they don't get adjusted. So using our new baseline score improvement of 20 instead of 0, these are our adjusted scores. Okay, so let me show you what this would do to the dot plot. You don't have to make this one, let me just show you. So I actually made the dot plot again, and then I went from 0 to 50. Because I didn't need any, we didn't have any numbers bigger than that for the adjusted scores. So for the online, here were the improvements. So I just plotted the values we got for the online kids. These are their adjusted scores. So 20, 24, 24, some 30s, some 34s, and a 40. And for the classroom kids, I plotted those too, the adjusted scores. So a couple zeros, some 4s, a 10, some 14s, and a couple 20s. So here's the point. Now that we made the adjusted improvements, it's obvious that the online scores are better than the classroom scores. And how do we do that? We basically treated every student as if they were like, as if we're comparing them to the geometry kids. So since they had a mean of 20, we were like, okay, well, what would that mean for pre-calc and for Algebra 2? And we adjusted their scores accordingly. So again, you don't have to make this. I just want you to see what that did for us. Now that we had the adjusted scores, we can compare like, oh, for sure, online class better than classroom. So that's my point. So if you use the adjusted improvements, the online appears to be a better course with a statistically significant difference. And that was probably also visible in the dot plot with the shapes. But now you can actually compare just online kids versus just classroom kids. Okay, so the last little bit for these notes, we're just going to talk about the definitions. So on this page, blocking in experiments, that's our new vocab word, blocking in experiments is very similar to the idea of stratifying in surveys. Notice I color-coded these. I'm going to say don't mix them up, but you'll probably mix them up. But that's a big hint for the AP exam. Don't mess up. Like, blocking goes with experiments. Like, that vocab term only belongs to experiments. Stratifying, that vocab term only belongs to surveys. So let's don't mix those up. Blocks like strata are not formed at random. We form them on purpose for a reason. So we pick the blocks. The best variables to block on are the ones that best predict the response. Okay, that's it for these notes. I will pick it up with the example and the activity tomorrow. I'll see you in class.